The first hurdle in making Mars habitable is its thin atmosphere. This thin layer of gases is not sufficient to support human life as we know it. Unlike Earth, where the atmosphere is thick enough to regulate temperature and protect us from harmful space radiation, Mars's atmosphere is a mere fraction of what we need. Mars's atmosphere is about 1% the density of Earth's. This means that the air is incredibly thin, making it difficult to retain heat. The lack of atmospheric pressure also means that any liquid water on the surface would quickly evaporate or freeze, making it impossible to sustain life as we know it. This thin atmosphere provides little insulation, resulting in frigid surface temperatures. On average, temperatures on Mars hover around -80 degrees Fahrenheit, but can plummet even lower at the poles. These extreme conditions make it challenging for any form of life to survive, let alone thrive. It also offers scant protection from harmful radiation. Without a thick atmosphere, Mars is bombarded by cosmic rays and solar radiation, which can be deadly to humans and other forms of life. Any long-term human presence on Mars would require significant shielding to protect against these dangers. To make Mars more hospitable, we need to thicken its atmosphere. This would involve increasing the amount of gases in the atmosphere to create a more Earth-like environment. A thicker atmosphere would help to trap heat, raise temperatures, and provide better protection from radiation. One proposed method is to release greenhouse gases trapped in the Martian soil and polar ice caps. These gases, such as carbon dioxide and water vapor, are known to trap heat and could help to warm the planet. By releasing these gases, we could kick-start a process of atmospheric thickening. These gases, such as carbon dioxide and water vapor, could trap heat and warm the planet. The greenhouse effect, which is responsible for warming Earth, could be replicated on Mars to create a more hospitable environment. This would be a slow process, but it could eventually lead to significant changes in the Martian climate. This process, called terraforming, would take time and significant energy. Terraforming Mars is not a quick fix. It would require decades, if not centuries, of sustained effort. We would need to find ways to generate and supply the necessary energy to drive these changes, possibly through nuclear or solar power. We could potentially use large orbital mirrors to focus sunlight onto the polar ice caps, accelerating the release of greenhouse gases. These mirrors would act like giant magnifying glasses, concentrating sunlight to melt the ice and release the trapped gases. This method could help to speed up the terraforming process. Another approach involves redirecting ammonia-rich asteroids to collide with Mars. Ammonia is a potent greenhouse gas that could contribute to atmospheric thickening. By redirecting these asteroids, we could introduce large amounts of ammonia into the Martian atmosphere, helping to trap heat and raise temperatures. Ammonia is a potent greenhouse gas that could contribute to atmospheric thickening. When released into the atmosphere, ammonia would help to trap heat much like carbon dioxide and water vapor. This could lead to a gradual warming of the planet, making it more suitable for human habitation. This method, while effective, poses logistical challenges and potential risks to any existing Martian infrastructure. Redirecting asteroids is a complex and risky endeavor requiring precise calculations and advanced technology. There is also the risk of unintended consequences, such as damaging any existing structures or habitats on Mars. Thickening the atmosphere would have several benefits. A thicker atmosphere would not only help to regulate temperatures, but also provide better protection from radiation. It would create a more stable and hospitable environment for future human settlers. It would increase atmospheric pressure, making it possible for humans to walk on Mars without pressurized suits. This would greatly simplify the logistics of living and working on Mars, as astronauts would not need to rely on bulky and restrictive suits for protection. It would also lead to warmer temperatures and the potential for liquid water to exist on the surface. Liquid water is essential for life, and its presence on Mars would be a major step towards making the planet habitable. With a thicker atmosphere and warmer temperatures, we could potentially see rivers, lakes, and even oceans forming on Mars in the future. Mars's thin atmosphere also poses a major challenge: radiation. Unlike Earth, Mars lacks a global magnetic field to deflect harmful cosmic rays and solar flares. This radiation poses significant health risks to humans, including an increased risk of cancer and other illnesses. One solution is to build habitats underground or within Martian hillsides. These natural shelters would provide shielding from radiation. Another approach involves incorporating radiation-resistant materials into habitat construction. Lead, water, and even Martian regolith can offer some protection. Developing advanced radiation shielding technologies is crucial. We could create artificial magnetic fields around habitats or develop specialized suits with enhanced radiation protection. Additionally, monitoring solar activity and establishing early warning systems for solar flares would be essential for Martian settlers. The long-term effects of Martian gravity on human health are still unknown. This is another area where further research is needed to ensure the well-being of future Martian colonists. Survival on Mars depends on establishing a closed-loop life support system. This system is crucial for ensuring that astronauts can live and work on Mars for extended periods without needing constant resupply missions from Earth. The concept of a closed-loop system is to create a self-sustaining environment where all necessary resources are continuously recycled and reused. This system would recycle water, generate breathable air, and produce food. Water recycling is particularly important because it ensures that every drop of water is used efficiently. Advanced filtration systems can purify wastewater, making it safe for drinking, cooking, and irrigation. Similarly, generating breathable air involves removing carbon dioxide and other contaminants while replenishing oxygen levels. Thankfully, Mars possesses resources we can utilize to achieve this. The planet's surface and atmosphere contain elements that can be harnessed to support human life. For instance, the Martian soil, known as regolith, contains minerals that can be processed to extract useful materials. Additionally, the thin Martian atmosphere, primarily composed of carbon dioxide, can be used in various chemical processes. Water ice exists beneath the Martian surface and within the polar ice caps. This ice is a vital resource for sustaining human life on Mars. By drilling into the ice caps or extracting ice from beneath the surface, we can obtain a steady supply of water. This water can then be purified and used for drinking, growing crops, and other essential activities. We can extract this ice and purify it for drinking, agriculture, and other uses. The process of extracting and purifying water involves several steps, including melting the ice, filtering out impurities, and ensuring that the water meets safety standards. This purified water is crucial for maintaining the health and well-being of astronauts. Electrolysis, a process that splits water into hydrogen and oxygen using electricity, can be used to generate breathable oxygen. This method is particularly effective because it allows us to produce oxygen on-site, reducing the need to transport it from Earth. The hydrogen produced during electrolysis can also be used as a fuel source, further enhancing the sustainability of the Mars habitat. Growing food on Mars will require innovative farming techniques. Traditional farming methods are not feasible due to the lack of fertile soil and the harsh environmental conditions. Instead, we must rely on advanced agricultural technologies that can operate in controlled environments. Hydroponics and aeroponics, methods that grow plants without soil, offer promising solutions. These systems use nutrient-rich water or mist to nourish plants, allowing them to grow faster and more efficiently than in soil. Hydroponics involves growing plants in a water-based solution, while aeroponics suspends plants in the air and sprays their roots with a nutrient mist. These systems use less water and space than traditional agriculture, making them ideal for the Martian environment. By optimizing the use of resources, we can maximize food production while minimizing waste. Compact farming systems can be integrated into the habitat, ensuring a steady supply of fresh produce for the crew. Martian soil, with proper treatment and nutrient supplementation, could also be used for cultivation. By adding essential nutrients and adjusting the soil's pH levels, we can create a suitable growing medium for certain crops. This approach allows us to utilize the abundant Martian soil, reducing the need to transport large quantities of soil from Earth. Recycling waste products is essential for long-term sustainability. Waste management systems on Mars must be designed to handle all types of waste, including organic, inorganic, and hazardous materials. By recycling and repurposing waste, we can reduce the environmental impact and create valuable resources. We can convert waste into fertilizer for plants and generate methane gas for fuel. Organic waste can be composted to produce nutrient-rich fertilizer, which can be used to enhance soil quality and support plant growth. Additionally, certain waste materials can be processed to produce methane gas, which can be used as a fuel source for various applications. This closed-loop system will minimize reliance on Earth for resources. By creating a self-sustaining biosphere, we can ensure the long-term survival and success of human missions to Mars. This approach not only supports the immediate needs of astronauts, but also paves the way for future colonization and exploration of the Red Planet. Section 4: Martian-made building with the resources at hand. Constructing habitats and infrastructure on Mars requires using the resources available on the planet. Fortunately, Mars possesses a wealth of useful materials. Martian soil, known as regolith, can be used as a building material. It can be compressed into bricks or mixed with binders to create concrete-like structures. Beneath the surface lies an abundance of valuable minerals and metals. These resources can be extracted and processed to create everything from tools and machinery to advanced electronics. 3D printing technology will play a crucial role in Martian construction. We can use Martian regolith and other materials to 3D print habitats, landing pads, and even entire structures. Utilizing local resources minimizes the need to transport materials from Earth, significantly reducing mission costs and logistical challenges. It also fosters self-sufficiency and sustainability for the Martian colony. Section 5: From barren to bountiful, cultivating life on Mars. Transforming the Martian landscape into a habitable environment will require the introduction of Earth life. This ambitious endeavor involves multiple stages, each more complex than the last, and will test the limits of our scientific and engineering capabilities. This process, known as terraforming, aims to create a self-sustaining biosphere on Mars. The ultimate goal is to make Mars a place where humans can live and thrive without the need for constant support from Earth. We can begin by introducing extremophile organisms, life forms that thrive in extreme environments. These hardy organisms are capable of surviving in conditions that would be lethal to most Earth life, making them ideal pioneers for Martian colonization. These organisms can help convert the Martian atmosphere and soil into something more suitable for Earth life. By breaking down the harsh Martian soil and releasing essential nutrients, they pave the way for more complex forms of life. For example, certain algae and bacteria can consume carbon dioxide and release oxygen, contributing to a breathable atmosphere. These microorganisms are the unsung heroes of terraforming, quietly working to transform the Red Planet. As the Martian environment becomes more hospitable, we can introduce more complex life forms such as plants and eventually animals. Plants will not only produce oxygen but also provide food and help stabilize the soil. These organisms will play vital roles in oxygen production, food production, and waste recycling. A self-sustaining ecosystem on Mars would mimic Earth's natural cycles, creating a balanced environment where life can flourish. Creating a self-sustaining ecosystem on Mars is a monumental task. It involves not just biological and ecological challenges, but also engineering and logistical hurdles. Every step must be carefully planned and executed to ensure the long-term viability of the ecosystem. It will require careful planning, experimentation, and constant monitoring to ensure its success. Scientists and engineers will need to work together using data from both Earth-based simulations and actual Martian experiments to refine their approaches. However, the rewards of a thriving biosphere on Mars are immeasurable. Not only would it provide a new home for humanity, but it would also offer invaluable insights into the processes that sustain life, potentially helping us better understand and protect our own planet.
Like and subscribe to start your journey today.